Welcome to the first video for Chapter 12 for your AP Statistics course. Today we will be talking about sample surveys. Remember, we're talking about generating data, good data that we can use for the different types of methods that we will be discussing later on in the course. Idea number one with sample surveys is examine a part of the whole. The first idea is to draw a sample. We'd like to know about an entire population of individuals, but examining all of them is usually impractical if not impossible. We settle for examining a smaller group of individuals, a sample selected from the population. Sampling is a natural thing to do. Think about sampling something you are cooking. You taste, examine a small part of what you're cooking to get an idea about the dish as a whole. I believe your book refers to taking a spoonful of soup from a pot of soup that you are making. As long as that pot of soup has been well stirred, taking a sample of just a spoonful should give you all the information you need about the seasoning of the soup as a whole. Opinion polls are examples of sample surveys designed to ask questions of a small group of people in the hope of learning something about the entire population. Professional pollsters work quite hard to ensure that the sample that they take is representative of the population. If not, the sample can give misleading information about the population, which leads us to bias. Sampling methods that by their nature tend to over or underemphasize some characteristics of the population are said to be biased. Bias is the bane of sampling, the one thing above all to avoid. There is usually no way to fix a biased sample and no way to salvage useful information from it. That's why we go over the proper methods for generating data right at the very beginning of this course, because if you don't have good data, there's typically not going to be methods to overcome that. You've just wasted your time. The best way to avoid bias is to select individuals from the sample at random. The value of deliberately introducing randomness is one of the great insights of statistics. Randomization can protect you against factors that you know are in the data. It can also help protect against factors you are not even aware of. Randomizing protects us from the influences of all the features of our population, even the ones we may not have thought about. Randomizing makes sure that on the average, the sample looks like the rest of the population, and we end up with what we call a representative sample. That's exactly what that means, is the sample represents the population by being similar to it on the average. Not only does randomizing protect us from bias, it actually makes it possible for us to draw inferences about the whole population when we see only a sample. That's what we will be doing next semester. Such inferences are among the most powerful things we can do with statistics. But remember, it's all made possible because we deliberately chose things randomly. Idea number 3 is it's the sample size. One of the questions we will be answering throughout the course is how large a random sample do we need for the sample to be reasonably representative of the population. It's the size of the sample, not the size of the population, that makes the difference in sampling. Okay, so whether you've got a small pot of soup that you're just making for yourself, or if you've got a huge pot of soup that you're making for a whole banquet, the same size of spoon is going to give you enough soup to test the small pot as well as the large pot, as long as both pots are stirred well. That's the whole key, is making sure that the soup has been stirred well, that had enough randomization, and you can use the same little soup spoon and test from the individual size pot or from the banquet size pot. Now, there is one exception. If the population is small enough and the sample size is more than 10% of the whole population, the population size can matter, and we'll get into that more later. The fraction of the population that you've sampled doesn't matter. It's the sample size itself that's important. Does a census make sense? Why bother determining the right sample size? Wouldn't it be better to just include everyone and sample the entire population? Such a special sample is called a census, and the U.S. government does that every 10 years, and it's a huge undertaking. There are some problems with trying to conduct a census. It can be difficult to complete a census. There always seems to be some individuals who are hard or expensive to locate or hard to measure. It may be impractical. For instance, for food, when you're manufacturing food, if I'm manufacturing a cupcake, I can't take a census of all my cupcakes to see how well they taste, or I won't have anything, see how they taste, or I won't have anything to sell. So you can't take a census there. You have to take a sample. Populations rarely stand still. Even if you could take a census, the population changes while you work, so it's never possible to get a perfect measure. If you were trying to get a census of the state of Texas during, even if you narrowed it down to a 2-week window, you were going to take a census of the state of Texas. Well, people would be born, people would die, people would move out of the state, people would move into the state, and so your census would be imperfect. Taking a census may be more complex than sampling. Populations and parameters. Models use mathematics to represent reality. Parameters are the key numbers in those models. A parameter that is part of a model for a population is called a population parameter. We use data to estimate population parameters. Any summary found from the data is a statistic. The statistics that estimate population parameters are called sample statistics. Okay, it's population parameters, both with a P, and sample statistics. So that kind of makes it nice and convenient to remember. Notation is very important for you to get used to. We typically use Greek letters to denote parameters and Latin letters to denote statistics. For the mean, your book uses Y bar. And the reason it uses Y bar is because it doesn't want you to think that X bar is the only thing that can be used. Just about every other textbook, your calculator uses X bar to represent a sample mean. And just about every other book in your calculator would think of each individual observation as an X. Your book thinks of each observation as a Y and the statistic of the average as Y bar. It really doesn't matter which one you use, but it's either usually X bar or in this one case Y bar, that is the sample mean. And then the Greek letter mu, okay, that represents the population mean. The standard deviation for the data is S, that's your statistic, and it estimates baby sigma, okay, that's lowercase sigma, which is the population standard deviation. And we go through, and for correlation, there's R for the statistic, and then rho for the parameter, lowercase b for the regression coefficient, and beta for the parameter. For proportion, there's a little bit of a difference there. We've got p hat for the proportion, that's a statistic, and p for the parameter. Okay, now we're actually going to get into the different kinds of samples. The first one, the one that is the most basic, but that works beautifully with our methods, is the simple random sample. So simple random samples are ones in which we draw samples because we can't work with an entire population. Keep that in mind. We need to be sure that the statistics we compute from the sample reflect the corresponding parameters accurately, because remember, we're calculating statistics from that data, from that sample, to estimate those population parameters. A sample that does this is said to be representative. We will insist that every possible sample of the size we plan to draw has an equal chance of being selected. Okay, if that's something that we want to make sure of, then a simple random sample is what we are going to be working with. Such samples also guarantee that each individual has an equal chance of being selected, because that's just a special case of our first statement there. It's just a case of a sample of size 1. So each individual, but also every possible sample of a particular size, has an equal chance of being selected. With this method, each combination of people has an equal chance of being selected as well. A sample drawn in this way is called a simple random sample, and that is the only kind of sample that can be abbreviated SRS. Even though there's another type that has the same initials, if you use SRS, you are referring to a simple random sample. In fact, there's a couple, but SRS means simple random sample. And SRS is the standard against which we measure other sampling methods, and the sampling method on which the theory of working with sampled data is based. Okay, it is the method that typically you want to use unless you have a good reason for bringing in another method. And we'll talk about good reasons that justify bringing in other methods. But simple random sample is the standard. To select a sample at random, we first need to define where the sample will come from. Okay, there's this theoretical population, but you actually need lists. You need to know what the individuals are. The sampling frame is a list of individuals from which the sample is drawn. And hopefully your sampling frame matches your population perfectly. That is the ideal situation. Once we have our sampling frame, the easiest way to choose an SRS is to assign a random number to each individual in the sampling frame. Samples drawn at random generally differ from each other. Each draw of our random number selects different people for our samples. These differences lead to different values for the variables we measure for those statistics. We call these sample-to-sample differences sampling variability. Some people call it sampling error, but that makes it sound like you've done something wrong. But if you read, if you come across the term sampling error somewhere, that means the same thing as sampling variability. Okay, so for example, all right, page 274. There are 80 students in an introductory statistics class. You are to select an SRS of 5. Well, one thing you could do is write down each student's name on identical pieces of paper, put them all in a hat, mix well, and draw out 5 names without looking and without replacement. In other words, you don't look at a name, write down the name, and put it back in. No, you draw out 5 slips of paper. It's important that you mix well and that you don't look, okay, because that's what ensures the randomness. Or you can assign each student a number 0, 1 through 80 and use a table of random digits. There is one in the appendices in your book, and I'll also be giving you a pink copy of that same table. Take digits 2 at a time, ignoring 0, 0, 81 through 99, and repeats. We ignore 0, 0, and 81 through 99 because those aren't assigned to any of our students. We assigned 0, 1 through 80. So if we draw 13, that represents a student, and that student would be selected. If we draw 87, that doesn't represent a student, so we would just ignore that and move on. Well, we're not really drawing, we're reading digits across the line of the table, but you see what I'm saying. If we come across the number 13, that represents a student. If we come across the number 87, it doesn't, so we ignore it. We ignore repeats because if you want to sample of 5 people, you can't have any one person being in that sample twice. So then you would keep selecting until 5 individuals have been selected. So let's use the digits provided in the example in your book. Okay, so we've got these digits that are kind of clumped into groups of 5, but we're going to take them 2 at a time. So the first 2 digits are 0, 5. That represents a student, so that student is part of our sample. The next 2 digits are 1, 6. 16 is part of our sample, so student number 16 is in. The next 2 digits are 6, and then we hop over to 2. 62 is in our range, so that it hasn't come up yet, so that person is included. So we've got 3 people so far. The next 2 digits are 93. 93 is out of our range. It doesn't represent a student, so we ignore 93. And then we move to 0, 5. 0, 5 is in our range, but student number 5 is already in the sample, so we ignore that one. Then we move to the next 2 digits, 77. That's in our range, so student 77 is part of our sample. And then 48. 48 is in our range, and that completes our sample. We now have 5 2-digit numbers that represent students that have been chosen. Or you can assign each student a number 1 through 80 and use your cast to generate integers between 1 and 80. You will need to ignore repeats. So the way that you would do this is you go to your scratch pad, press menu, choose probability, choose random, choose integer. In the parentheses, enter 1, 80. Make sure you put the comma. Press enter and keep pressing until you have selected 5 different students. I suggest that you pause the video right now and actually practice this because you're going to have to know how to do it. Okay, so go practice. Alright, did you practice? If not, stop the video and go practice. Seriously, go back and practice with your cast. Okay, stratified sampling. This is the last topic we're going to do on this video, and then we will switch to the second video. Simple random sampling is not the only fair way to sample. More complicated designs may save time or money or help avoid sampling problems. All statistical sampling designs have in common the idea that chance rather than human choice is used to select the sample. Designs used to sample from large populations are often more complicated than simple random samples. Sometimes the population is first sliced into homogeneous groups called strata before the sample is selected. Then simple random sampling is used within each stratum, that's the singular, where strata is plural, before the results are combined. This common sampling design is called stratified random sampling. Notice that its initials are SRS, but it's never referred to as SRS. It's referred to as stratified random sampling. The most important benefit in stratifying is that stratifying can reduce the variability of our results. Okay, so it's going to give you more consistent results when you do that. It reduces the variability. So it reduces your sampling variability or your sampling error. When we restrict by strata, additional samples are more like one another, so statistics calculated for the sampled values will vary less from one sample to another. So stratified random sampling can reduce bias. They can keep subgroups of your population from being overrepresented in your sample. If you think that there's a particular variable that is critical in people's response to the survey, you might want to stratify according to that variable. Stratified sampling can also help us notice important differences among groups. So there are valid reasons for using stratification. Okay, this is where we're going to pause and move on to the second video. So I will see you guys again in video 2.